today we will discuss read and write assist circuits in 60 SRAM. These are important because of the stability issues and because the issues in writing and read disturb etc., which we had discussed in the previous lectures. This lecture is a part of module 5. First we will discuss what is the need for read and write assist circuits, and then we will discuss write assist circuits, compare different kinds of write assist approaches, and then we will briefly discuss read assist techniques. So, suppose you are writing in a memory 60 SRAM cell. Suppose N1 and N2 are the two nodes of the 60 SRAM cell. So, this is the 60 SRAM cell. Suppose this N1 and N2 and we are writing. So, how are we writing? We are keeping this VDD, this is initially, and this we are keeping at 0 for writing. So, N1 is connected to 0 bit line. So, BLB So, N1 is connected to BLB through the access transistor and N2 is connected to BL through the other access transistor, left side access transistor, and N1 stores VDD or is high, N2 stores 0. So, in this case N2 is pulled up, N1 is pulled down. As we know that there is a metastability point which must be crossed before the switching to happen. So, we are referring to this metastability point. So, this metastability point needs to be crossed. So, in static transfer characteristics we see a metastability point which is also called separatrix. So, the dynamic value could be a little different from the static value, nevertheless it is quite close to the static value. So, if that value is not crossed during the word line width, so this is the word line pulse, okay. So, this we can call word line pulse width. So, during the word line pulse width, so this is, so during the pulse word line pulse width, if the change in voltage of N2 is not, so N2 is to the access transistor, it is connected to VDD. So, if the change in voltage of N2 and change in reduction in voltage of N1 do not cross this separatrix, in that case switching would not happen, otherwise the flipping of the data would happen, and that is what we want in write. And we can see it this way also. So, this is the through dynamic simulations, this I am showing in static. So, static separatrix or metastability point could be different from the dynamic value. So, here this is for dynamic simulations, transient simulations or transient measurement of dynamic properties. So, what is this WL critical? WL critical or word line pulse width critical is that value at which the minimum pulse width, minimum word line pulse width, which ensures flipping of N1, N2, QQB. Okay. So, this is what is how we define WL critical, and in that what you observe is that if you have a pulse width which is slightly larger than WL critical, in that case Q and Q bar, for example, you can see here Q and Q bar. So, this is the value N2. N2 is switching from 0 to 1, 0 to it is crossing it 0 to 1, and N1, N1 is switching from VDD to 0. So, that is what is happening, and in case you have a word line pulse width which is just smaller than word line WL critical. So, it is 1 picosecond smaller than that. What you observe is that N2 does not switch, it increases and falls like this. Again, there is just a glitch there, and N1 also does not change state. So, this is the separatrix. Now, this dynamic separatrix could be different from static separatrix or metastable point as you call. So, for writing we need, and what we observe is that as you reduce the supply voltage, the word line pulse width keeps on increasing, and it increases to for example, from 1 volt to 0.7 volts it is increasing to 10 times. Whatever was the word line WL critical value here, it has increased to 10 times for a 32 nanometer node. So, these are measurement results on commercial SRAM cells. And why is the word line pulse width increasing? Because as you reduce the voltage, one of PMOS and NMOS, it becomes weaker as we reduce the voltage, and therefore, it becomes difficult to flip the cell. So, what we observe is scaling of supply voltages or scaling of technology increases the word line criticals value, and therefore, and this is all there in this paper. So, the previous results that I was discussing are also all discussed in this paper. So, what we observe is that as you scale the supply voltage value, the SRAM writing in an SRAM cell becomes difficult, WL critical increases drastically, and there is also an issue that device mismatch also increases as the both technology scaling as well as reduction in VDG, supply voltage, and therefore, there is a unpredictability with respect to the value of WL critical that you have extracted. So, to increase these margins and also to increase the writability, write assist circuits or write assist techniques are resorted to. So, we will discuss a few of these write assist techniques. So, the one of the write assist technique is to reduce the VDD of the SRAM cell. So, you are not reducing the VDD of word line or bit lines, you are just reducing the VDD of the SRAM cells in the array. Okay. So, what does that do? Now, suppose you are having Q at a value VDD and QB is 0, initially this is 0, and later BL you are keeping at 0 and BLB you are keeping at VDD to write for the write operation. So, what would happen? Q would be discharged. So, if you reduce the VDD of the cell, you need to discharge from a lower value. So, the overall charge on the capacitor here is now smaller because of the reduced VDD cell. So, that will discharge Q faster. Once Q is discharged faster, M4 would be turned off earlier. If M4 is turned off earlier, QB would be charged earlier, that would put off M3 earlier, and the overall process would become faster, as we can see here. So, this has VDD cell has reduced while the word line is asserted high, and BL is put to 0 here, and QB. So, you can see that now the high value is now lower because VDD cell is lower, therefore, Q which should be at VDD is at a lower VDD cell. So, this one is now at, instead of being at VDD, this is now at VDD cell. So, therefore, the amount of discharge that is to take place reduces. So, that makes the entire process faster, and therefore, your WL critical reduces. Another technique is to increase VSS. This also works on a similar principle. You have increased VSS, So, what does that do in the earlier case? So, this would now be at VDD, this is 0, and instead of QB being at 0, this is at VSS cell, which is a higher voltage, and this is at VDD. So, you need to charge QB to a higher value, and you would be charging the value of QB to using a smaller amount of charge. So, this would happen faster. Since M3 discharges earlier, Q would be discharged faster, that would turn on M6 earlier and turn off M4 earlier. So, the entire process of flipping would happen earlier. So, writing increases, the speed of writing increases. So, here VSS cell is asserted high with the word line being high, and you can see that QB is now to be charged from a higher value, like it is here. See, it is charged from a higher value, and the other side would also be charged to a higher value, in the sense that this would not turn 0, this would go to Q would go to VDD cell, but then after you again turn this back to 0, VSS again you turn it back to 0, this would get discharged, but your writing has happened faster. What you can see here is that the metastability point or separatrix also moves. So, how does that move, that we can just see for an understanding. So, this is the if this is without the right assist circuit, if this is the butterfly curve, then with the right assist circuit, how would it look like? Now, 0 is affected, so 0 goes higher. So, if we with right assist circuit, if we use a different color, this is with right assist. This is with right assist. So, we can see that the metastability point has moved, or separatrix has moved, and the separatrix has moved to a higher value of Q and QB. So, if it has moved to a higher value of Q and QB, then you can do the discharging more easily, because you would be requiring to discharge QB, this Q to a lesser extent. So, discharging Q to a lesser extent, and charging QB is now easier because already its value is high, and you need to discharge Q to a lesser extent. This has moved to a higher value. So, the flipping, actual flipping would happen at a higher value of the metastability. Metastability point is at a higher value now, Q, QB both assume a higher value, and therefore, you need to discharge Q to a smaller value. To the discharge of Q, that how much charge is to be taken out, is now smaller. So, it would happen faster due to this reason also. How are the power supplies managed? So, you can have an LDO or whatever, some power management system locally to the cell, so that VSS cell is higher, VDD cell is lower, whatever technique we use. So, there are other techniques also, like word line boosting. So, here you increase the word line voltage. So, if word line voltage is increased, obviously while discharging, for example, if you are having this at VDD, this is 0 and this is, suppose, or let us take the opposite example, this is VDD, this is 0 and this is 0, this is VDD for writing. So, if you boost the word line voltage, there will be smaller drop across M2. So, Q would have, for the same current to flow, Q would have a higher value, and if you boost the word line voltage in M5, there will be a smaller drop. So, therefore, QB would be closer to 0 for the same current to flow from M6 to M5 while the flipping happens. So, therefore, the flipping happens faster with word line boosting. But the problem is that even those cells in the row, so in this row you would have cells, another column of BL1, suppose this is BL0, BLB0, So, you will have BL1, BLB1, another column controlled by the same word line. It would have cells which are controlled by the bit cells which are controlled by the same word line. So, you have boosted the word line. So, this word line, because it is boosted now, it would read, okay, and while reading again the discharge more discharge would happen. For example, if you are reading a 0 here, so more discharge of BL1 would happen and a more discharge of QB would happen. This can actually flip while reading. So, these kind of issues can have, these are so half selected, so these are called cells can get flipped. So, this issue is there with word line boosting, this is techniques. Likewise, so with word line boosting, what do you observe? As you reduce the supply voltage, this is without word line boosting and this is with word line boosting, the WL critical is quite improved. So, there is another popular write assist technique which is negative bit line. Now, this negative bit line can be generated using some capacitive coupling techniques, biasing techniques. So, if one does that, what do you observe? Since this is negative bit line, it is in principle similar to word line boosting, VGS of M2 increases. If suppose BLB is 0, BL is VDD, QB is VDD and Q is 0 and you are writing. So, the VGS of M5 it increases. So, that would make the and VGS of M2 it initially is the same, but after writing it increases. So, this VGS this would increase. So, this would get discharged faster and therefore, flipping would happen earlier. But this also has this problem that in the column other cells in the column are affected, because in the column you have other SRAM cells and those other SRAM cells would have, because their word lines are 0. So, the other SRAM cells in the column, suppose you have these SRAM cells and so this is cell 1 and cell 1 is being you are selecting the word line of cell 1. So, you are writing in this, but cell 2 you are not selecting the word line. So, you do not want to write in this, but the VGS of the access transistor M5 increases even for cell 2, because its source voltage is now smaller than 0. Because of your negative bit line. So, it would start leaking. So, you may have a flip because of the leakage through the M5 of this unselected cell. So, these kind of issues are there with this negative bit line technique. So, without negative bit line, if this is the right margin, then the right margin improves significantly as you use the negative bit line technique. That is what is observed in this paper. So, right margin comparison with different write assist techniques was discussed in this paper, and you would see that in general the right margin would improve with negative bit line, and that is, and it happens across technology nodes, and this is with rising VSS, lowering VDD, bit cell VDD and boosting word line. So, all the techniques they have compared. What about read assist techniques? So, as we have discussed with write assist techniques, the read noise margin is affected. So, as you use different write assist techniques, you find that the read noise margin reduces, as we had discussed with word line boosting, the read noise margin reduces. Likewise, static noise margin also affected and it also gets reduced because of the write assist techniques. Because of the leakage, one of the, for example, if you use negative bit line, then one of the access transistors has a very large leakage. So, that would skew the cell and the static noise margin would reduce. We can understand it this way, that the butterfly curve, instead of being like this, can turn, because of the skewing, it can it can become skewed, and that would reduce the noise margin, because then the static noise margin would be the largest square that can fit in this. So, that would reduce. So, negative bit line can actually cause this issue. So, read assist techniques opposite to the write assist techniques. So, in some sense, instead of over driven word line, you would have under driven word line, so that reading does not disturb Q and QB as we, and lower bit line boosting VDD, this would be similar. So, with suppressed word line reducing VDD, there is an improvement in the static noise margin, as we can see. So, likewise read static noise margin also with suppressed word line is improved. So, in this lecture we discussed the importance of word line write assist techniques in some detail, and briefly read assist techniques, why they are important in near threshold voltage domains and with technology scaling, scaling of supply voltage, and then we discussed 4 different approaches of write assist techniques and their limitations, their importance, and also we briefly discussed read assist techniques. Thank you.